Okay, so right. So today we're going to speak about the Lebesgue integral, and we're going to motivate why the Lebesgue integral is needed. So let's start with a quick refresher. So remember that the Riemann integral, or maybe I'll start with some motivation. Now remember that one of the key concept in probability is random variables. So essentially, a random variable is a function from a probability space to the numbers, the real numbers, and many times we want to talk about the average of the random variable. So we have two cases typically. One is a discrete case where the random variable will have some discrete values, say AI. So in that case, the average is the sum of AI times the probability of the random variable getting the value AI. Okay. So that's that's going to be the average of the random variable in the case that the random variable has infinite uncountable number of possible values. We call this the discrete case. And then the continuous case. In the continuous case, we have a density function. So the average is the integral of the value of the random variable times the density function from minus infinity
to plus infinity.
Okay, so that's the average. So we need and as we talk about probability, we talk about random variables, we talk about averages, then we talk about variances, which is another type of average. Also, we get to an integral, and so on. So we need we want two things. One, if you maybe you notice many times the same arguments are made for these two cases in probability. So because this side here seems to be different than the one on the left. And the one on the left is an integral. The one on the right is a sum. So there's the entire probability theory has two arguments: one for the discrete case and one for the continuous case. So it would be really nice if we could have one concept that will let us say things one time. That we don't need two cases, just one argument for both cases. For that, we need one concept that will include this and this as well. And that is something that the Lebesgue integral enables. Now the other thing, and that's the thing I want to, so with the Lebesgue integral, we can talk about averages regardless of, in the same way, regardless if they are discrete or continuous, which is really nice, but it's also very, it gives you insights about what is really important in the probabilistic argument. Now, the other side of this is that this is, if you take the Riemann, usually we use the Riemann integral to define integrals. And if you think about the Riemann integral, then the functions that are that you can define the Riemann integral for are smaller than the functions, the smaller set than the function that you can define the Riemann integral, the Lebesgue integral for. So essentially, going to the Lebesgue integral will let us talk about many more functions and do their integral. So we'll be able to expand our discussion in terms of an analysis in terms of probability theory and statistics and then machine learning to a larger set of things, basically. So what I want to concentrate now is at a more technical level is to show you how, in a very simple case, if you understand the idea of the Lebesgue integral, immediately you can integrate more functions. So you know that the real numbers, they are divided into two sort of numbers. There's the rational numbers and there's the irrational numbers, right?
Yes.
Right. And the
Rational numbers are discrete, right?
yeah, so rational numbers are numbers of the sort m over n.
Yeah.
Where m and n
is yeah
are a natural number, okay?
natural number. Yeah. I think one question here: the density function you mentioned, like the dx, fx dx. Right.
Keep going.
So,
keep going. Yes.
Yeah. So for the numbers which are not discrete, which are continuous, in that case we are using the density function, right? But for the discrete numbers, we are not using any density function. Is that like so? Like, was the thought process like that?
Yes, but the question is whether we can think about the density function and the probability for each possible value in the discrete case in the same way. Okay? And it turns out that we can, and actually that's part of the trick that makes the Lebesgue integral attractive. So essentially, if you think about this, they're saying the same thing. So the density function is saying how the probability mass is spread, and also the probability of x being at a certain point also say how the probability mass is spread. It's just that, okay, they're saying the same thing. The difference is not a fundamental in some sense. Okay.
Okay.
So we want, yeah. So we want a way to talk about them in the same way because they are essentially the same thing.
Okay. Got you.
Great. So So this is and the irrational number, like for instance, the root of 2 is irrational. Okay. And so on. So irrational numbers are numbers that cannot be described as by dividing two natural numbers. And one thing to understand about the rational numbers is that the rational numbers are countable. Okay, you can take they're very small actually. You can take them and you can order them in a series. So they are small. They are countable. And the rational numbers are very big. Okay, so most of the numbers are rational numbers, are irrational numbers, not rational numbers. That's one intuition. Now, one of the things I will say now without proving. So, if you think about the segment, say the segment between 0 and 1, including the endpoint, okay? So what's the length of the segment?
0 to 1.
Yeah, so the length of the segment between 0 and 1 is 1, right?
1. If it is rational.
Doesn't matter. I'm talking about the entire all of the numbers between 0 and 1. Okay.
Okay.
So the length of the segment between 0 and 1 is 1. Okay. Now, so one of the ways to think about the uniform probability on 0 and 1 is if I take here like a segment of length a quarter, and then I throw a number, I throw some point randomly. What's the probability that it will fall in? I throw a point randomly on the segment 0, 1. What's the probability that it will fall in a segment with length a quarter?
1 by the count of the total numbers from 0 to 1, the integration of the all the numbers, right?
So
Like
the length of the segment between the small segment is a quarter, and the length of the entire segment is 1. So the probability is just a quarter.
length of that segment is 1/4 of the total length.
Yeah. So if
Okay.
if I throw a point in the segment between 0 and 1, then the probability of the point falling in that segment is just a quarter. Okay?
Right.
Okay, very good. Now, but what is your intuition? What's the probability of choosing a rational number in the segment 0, 1? So I'm throwing a number on randomly on the segment 0, 1. What's the probability that it will be m over n? And a hint is this is my hint to you.
Yeah. then we are searching for a rational number to
No, not searching. We are throwing a
Throwing
point randomly in the. So this is the segment 0, 1. You see here 0. Segment goes to 1. Okay.
Okay.
Now there's this. It's like a thought experiment. There's this guy here. You see, and he randomly throws a point here.
Right.
What's the probability that you'll get some number of the form m over n?
Okay. So so what is the probability of that number being a m over n? Right.
Yes.
So m by m over n divided by, as 0 to 1 we are having segment 1, so m over n by 1.
But m over n is just a point.
Well, we know it's not 100% because you could have like a third, right, which would be irrational, right? So
no, we said most of the numbers are irrational.
Irrational, big, in the big set.
Yes.
So it might be like it would be obviously the infinite number of irrational numbers, right?
Yes, there's
So
an infinite number of rational numbers. There's infinite numbers of irrational numbers, but the irrational numbers is a much bigger infinite.
Right. So it might be an integral of 0 to infinite and m over n into the density function.
No, we don't have a density here. We don't have an integral here. We just need intuition without any technique.
So is it only even fractions that are rational?
No, rational are all numbers of the form m over n. So
right, but I'm trying to figure out which subset in here. So we know like a quarter, an eighth, you know, all the things where you're
they don't contain a length. They're not a segment.
Okay.
Like between any two irrational numbers, you have a rational number. Between any two rational numbers, you have an irrational number. You see, they're not a segment.
Okay. So it might be a rational number also. It might be a rational number also. It might be irrational number also. We don't know. There is a problem. Like
it might be an irrational number. It might be a rational number.
Exactly.
So let me
Eitan, one question. Like for the example,
let me ask you a question. Do you think the probability is 1?
The probability?
Do you think the probability is 1?
No, because it will always not be the number I desired. So obviously there is a chance factor. So obviously the probability will not be 100%.
Do you think the probability is 50%?
50.
1 by 2.
1 by 2. No, because
we said the rational numbers is smaller, right? Much smaller.
Right, because there are a huge set of numbers. If we consider the irrational also at a big chunk, so we cannot say there are two numbers, so my chance is 50%. Like kind of, I'm thinking from probability perspective. Please correct me if I'm thinking very dumb. That I have a white ball and I have a red ball in the basket. So to choose the ball, shall I get a white ball? It is chance 50%. So not like that. So obviously it should not be 50% case.
Yeah, it's not. So the chance that you find a rational number is much smaller. How small?
Exactly, obviously, because the set of rational numbers between 0 and 1 is less rather than irrational numbers.
Yeah.
Yeah.
So the answer is 0. The
Tends to 0.
surprising answer is 0.
Yeah. Yeah.
The chance that you get a rational number is
Yeah.
is just
It's 0.
0.
True.
And maybe later on I will. It's very easy to show it, but I don't want to. I just want. I'll go back to this at a later stage. I want to get to where I wanted to go. So essentially, because the chance of choosing a rational number is 0, the length of the set of rational numbers in the segment
0 to
0,
1.
1. What?
Yeah. In the segment 0 to 1 is 0.
Yeah, is 0, exactly. So what is the length? What is the length of the?
You wrote it 1. Eitan, you wrote it 1.
I wrote 1, so I'll fix it. It shows that you're listening to me. Thank you. So the set of irrational numbers in the segment 0, 1 is then what? What do you think?
Irrational number is it is infinite.
Right, but what's the length of the irrational numbers in the set 0, 1? If the length of the rational numbers is 0,
It has to be 1.
Yeah, it has to be 1 because exactly.
Yeah.
Because the entire entire length is 1. So you see the
100%.
length. Yeah. So the length is
100%
captured. Yeah, exactly. So the length is captured by essentially by the irrational numbers, not the rational numbers. In an intuitive way, the length is a concept that is doesn't change up to a countable set, basically. So now we get to the interesting thing, basically. So if you remember, an integral of a function is obtained by what is called the Riemann integral is obtained by what is called the Riemann sum. So if I want to know what the integral is between a and b, the way I do this is I divide it into segments, and then I take some point of the function here, and I take the length. Okay, so if the length here is a1, so and this is the length here is a2, so on. So and the function here, I'll call it fa1. I can take any point in the middle. So the Riemann integral is basically I take the sum of ai times ai, and as I make the ai's smaller and smaller, I get the integral.
Yeah.
That's the integral.
Yes.
Now,
Yes.
okay. Now,
Yes.
the interesting thing is the following. So the following function, I define a function that looks like that. The function is 1 for the irrational. And 0 for the rational.
Function equals to 1 when it is irrational and 0 when it is rational. Okay.
Yeah.
Binary function.
Yeah. So such a function, it doesn't have a Riemann integral. The integral is not defined. Why is that? Because if I take those rectangles, then
Yes.
if I take the ones, in any segment, there's both irrational and irrational, both rational and irrational numbers. So I can take either 1 or 0. So the limit here is not defined. It can go either to 0 or to something else. Okay. So there's no Riemann integral for this function.
Ethan couldn't understand the last point you mentioned, that we cannot take any limit here. If you could please explain again.
Because here, when you look at A1, you have here in this segment, you have a rational point and you have an irrational point, because any segment has both rational and irrational numbers.
True.
So the function here in the segment A1 can be either 0 or 1. So when I take here, I can take either 0 or 1 throughout. So either it goes to 0, because it's 0 times A1, 0 times A2, 0 times A3. Okay?
Correct.
Or it goes it's basically A1 plus A2 plus A3. Okay?
Correct.
So there's no limit, basically. There's no limit. So,
that means like I can go. Yeah, I can break it onto as many number of rectangles I want, so that there is no limit. That's what you are telling.
No. The reason there's no limit is because I can set the FAI to be something totally different. I can set it to be either 0, and I can set it to be 1.
Correct.
So if I set it to 0, you'll get 0. You'll get 0 times A1.
Correct.
Plus
0 times A2 plus 0 times A3.
Yeah, exactly, and that will go to 0.
Right.
And if you go 1 times A1,
A1, A2, A3, A3, like that. Yeah.
yes, that will go to 1, because we're talking about the segment 0 to 1. So we have here A being 0 and B being 1. Okay.
Right.
So it goes to two different limits. So the integral is not defined. Okay.
Correct.
Now, the idea of the Lebesgue integral, this is the punchline, is to look, instead of looking at the domain of the function, we look at the range of the function. So the range of this function is 1 and 0, right? These are the two values that the function can give. Okay.
Yes, 1 and 0, two variate function. Yeah.
So if we look here, and so we look, there's 1 and there's 0, and we can ask ourselves what are the values that are getting us to a 1, and what are the values that are getting us to a 0. Okay, so all of the values that are getting us to a 1, we call it f minus 1 on 0, 1. These are the irrational numbers.
Right.
Because the irrational numbers goes to 1. Okay.
Hmm.
Oh, and all of the values that are getting us to a 0. So
Rational
f
numbers.
-1, yeah. Of 0, that's the rational numbers. So the way we do this in the Lebesgue integral, we divide the range of the function instead of the domain of the function. So the integral is the limit of the sum of the value 1 times f minus 1 1 plus the value 0
0
times f
times
minus 1 of 0.
0.
Okay.
Hmm.
Now, I need to be precise here. I want to say the length of f minus 1 and the length of f minus 0. The way I did here was taking the length of a1. So the length of f minus 1, remember what did we get at the length of the irrational is?
1.
1. And the length of f minus 0 is what?
0.
F minus 0 is the rational, is 0. So this is 1 plus 0. So it's 1. So you see an example where I don't have a Riemann integral, but I have a Lebesgue integral. And the idea of the Lebesgue integral is to divide the range of the function instead of dividing the domain. And once you have the Lebesgue integral, then you can develop probability theory with just one notion for the average, because these things here, the fx and px, they are treated in the same way. They're treated as what they call a measure, or because the probability mass is a measure. But what the takeaway from this is that we have an integral that instead of dividing the domain, divides the range. And once it's dividing the range, everything becomes much more simple. That's the message.
So in any domain, when you are searching for a particle to be existing, or the probability of the particle, so if we go by range, then finding the probability of that particle will be easier. That is the notion, right?
Finding the average will be sometimes easier. Yes.
Oh, okay.
Yeah, we talked about the averages, right? We're calculating averages.
Right.
Yeah. This is also important in Bayesian analysis, because Bayesian analysis also needs to calculate integrals as well for other reasons, not only averages.
Okay. And Eitan, Riemann integral. Riemann integral is talking about not the range, right?
So the integral, the Riemann integral is talking about the domain. So it's dividing the domain into the rectangle. Yes.
Into the rectangles, yeah. Like
yes.
The full domain into as many as possible granular rectangles, so that we can measure the area and do the integration, like width into length.
Yes. In contrast, the Lebesgue integral divides the range.
Divides the range.
Yes. And then you have to take the f f minus 1 function to get the sum and then to get the integral. So it's the same idea, but dividing the range instead of dividing the domain.
Okay, Ethan, one question here. Why are you calling it f minus 1?
Because it's all of the points that will give me a 1. So the irrational numbers are all of the points of f that will give me a 1, because that's the way I define the function. So f minus 1 of 1 is the irrational numbers. F minus 1 of 0 is all of the points that will give me a 0. And I defined it to be the rational. So f minus 1 of 0 is the rational.
Got it. Yeah.
Great. Any other questions or thought?
Any implementation of this process? Can we have some? We can search it over internet and some books also. Some applications I would like. It would be great that if we could do some application on it.
Try to look for like if you like to play with integrals, look for Monte Carlo.
Okay.
Monte Carlo methods.
Okay.
And try to use it to define the averages.
Okay.
Of different things.
You mentioned Monte Carlo.
Yeah, Monte Carlo. Just look for Monte Carlo.
Okay.
Monte Carlo methods, and try to calculate some average of a random variable using Monte Carlo.
Okay. Okay.
Just to get a feeling how you can practically calculate averages of random variables.
Okay. Okay. Great.
Okay. Any other thoughts or comments or questions? Okay, so thank you very much, and we'll continue next week.
Sure. Thank you so much, Eitan.
Thank you
for this. Yeah.
Thanks.
היי איתן.
היי, מה נשמע?
בסדר.
תן לי רגע לשלוח משהו פה. רק רגע. סבבה, יופי. אז רוצה שנדבר קצת על ה-heatmap paper, או על דברים אחרים? איפה? על מה אתה רוצה לדבר?
לי משהו מיוחד בינתיים, פשוט קצת בעיות מחשב.
אז בעצם אני חושב אולי כיסינו את רוב הדברים עד לפני הפגישה, נכון?
כן, אוקיי.
זאת אומרת, אני צריך לקרוא את ההיטמפ, יהיה פגישה עם פריז'ת, ואז אנחנו... ואני חושב שעשינו בריינסטורמינג על רוב הדברים.
סבבה.
אה,
אוקיי. טוב,
אוקיי,
אז
אז
זה
אני
אני.
שומר אותך לנצח את המחשב, נראה לי.
כן. שונא את הדברים האלה.
כן.
טוב,
טוב, בהצלחה,
תודה.
נדבר.
ביי.
ביי.